today. He is at UPenn, I think. So I'm here to cover the lecture today. And honestly, he kind of gave me a bad deal. He gave me like the driest lecture of the class. So please bear with me, and hopefully I can make it a little fun for you all. So just to remember what we went over last time we had a discussion about the online gradient descent algorithm and the framework of online convex optimization. And we had a few definitions from before. I just want to reiterate them. They'll be useful today. So convexity, or this is also called Jensen's inequality, or Jensen's inequality. I don't know which one. So f is convex if for any points x and y, if I take a point on the line between x and y, that's less than or equal to if I took that weighted sum of their function values. So what does this mean graphically? The stereotypical kind of convex function you should always have in mind is the quadratic function, the parabola. And what this statement says is that if I take any 2 points, let's say x and y, right? And now I take any point here, the line between them, since x and y are both one-dimensional, is just like any point between x and y. Notice that the line connecting the f values, right? So the line connecting the two f values of these functions sits above the function value. So this is the kind of picture you should have in mind of your stereotypical convex function. And also a theorem, we went over this last time too, I think, kind of the first order approximation. So what does this right-hand side encode? It encodes the tangent at x. And it says if you take the tangent at x and you trace it out to where y is, it lies below the actual function value of y. So if f is differentiable, you can show that this is equivalent to being convex. And then the final definition was Lipschitzness, which is just saying how fast a function can grow. So f of x minus f of y can only grow g times the difference in the arguments. And again, if f is differentiable, this is equivalent to the gradient having norm at most g. So yeah, these are the definitions from last time we're going to use. And today I want to start by talking about a few more definitions. Actually, let me give you first a kind of flavor of where we're going. So yesterday we talked about, or Tuesday we talked about online convex optimization, which was about having different convex functions that are constantly coming in online that you have to try to play well against. Here we're going to work in the framework of regular convex optimization, or offline convex optimization, where the function is fixed, and we're going to try to minimize it. And we will work with a convex function, and we will work over a convex set. And maybe to give you a flavor of why you care about this problem, right? Because Professor Azani loves giving examples. So offline problems are still very interesting. So if you remember before, we were talking about the flow polytope, right? We were talking about we want to route paths and graphs, and one way to think about choosing a distribution over paths was the flow polytope. People also ask other questions about the flow polytope, like what is the point in the flow polytope with the minimum cost? This is something people care about. This is called min cost max flow. And there was this remarkable kind of achievement in this problem in, I think, 2022. I think it was something like Chen, Kale, Li, Peng. See, I only wrote down the letters, so these two other authors, sorry, I don't know their name. But these folks in 2022 were able to solve this problem in, if you were working on a graph with let's say e edges, they were able to solve the problem in e to the 1 plus little o of 1 time. You may have heard of this. This was called near linear time max flow. And this was like a big, big achievement in computer science. Just to remember, like what is like Ford-Fulkerson or these typical algorithms you learn in undergrad, those are something like e squared e cubed. So this is like a massive, massive improvement. This was like a big kind of theoretical win. And how did they achieve this win? They achieved this win by first relaxing the problem to a problem about convex optimization, about a continuous function over a continuous space. And then they used more sophisticated optimization methods to achieve their answer. So here today we're going to talk about gradient descent. But in this work, they used what are called interior point methods, which I don't think we'll talk about. But they're kind of like, think about, gradient descent is your first kind of foray into optimization. If you go deeper, you'll find these other methods called interior point methods. So I just wanted to give a little bit of a why you should care, maybe. Of course, gradient descent is used all over the place. It's used to optimize neural networks. It's used to optimize all sorts of learning models. Great. So let's talk about gradient descent now, offline gradient descent. So the pseudocode I'm going to write is going to be nearly identical to the one you saw on Tuesday, but our analysis is going to be a lot different. So give me a second. Yeah, there's an attendance sheet going around. Yep. Yep, right here. So we're just going to in a loop. Compute the gradients at xt and subtract them times some learning rate parameter, which can change throughout time. We'll talk about how to change it throughout time. And then we return the average, or sorry, the best one we've seen. I think you can return the average too, but today our proofs will be about the best one. Yeah, and again, notice the only difference from Tuesday is that there's no t subscript on the f. It's the same function we're trying to minimize throughout time. All right, cool. Any questions about what I just wrote here? Yeah? Yes. Yeah. So we will talk about if we want to change it with time or not, depending on our different functions we're analyzing. Yeah? X bar, I mean, just return the minimum. You can also return the average, I think. And by convexity, the proofs will work. I think our proofs today are going to work on the argument. Yeah? Because maybe your last step, like your last iterate is like bad. Like maybe like your optimizer was doing really well, and then for some reason, for one step, it went off course, and that happened to be the step you ended at. Yeah, so I'm saying, like for this specific optimization algorithm, we can prove what's called a last iterate convergence guarantee. You can't prove that always, and so you might want to return the average instead. Yeah. Yeah? Yeah, for some optimization algorithms. But gradient descent, we know how to do last iterate. Yeah. Or not, I guess this is not last iterate, this is like the best iterate. But yeah. Yeah, there's also something to be said about generalization. Like if you're doing this to train, the function is a neural network, and you're trying to find the best parameters, maybe you don't want to take like the best thing for the training data. Maybe you want to take an average over your training. Yeah, so different use cases. But for today, we'll focus with this in our proofs. And to talk about places where gradient descent converges and how fast it converges, I want to introduce some new definitions. Yeah. We're not taking the average. I just said you could take the average in some other context. Yeah. Okay. Anyways, so yeah, let's talk about some cases when gradient descent converges. So I'm going to define 3 more things. So a function is called strong convexity. So f is alpha strongly convex if, let me make sure I write this correctly. So it's almost, it's a stronger condition than convexity. So convexity says that f of y is at least f of x plus the gradient of f times the difference. And strong convexity is saying something further. It's saying that there's actually like an extra little bit that it's convex. Okay, and I'll give you a graphical intuition for this in a second. But yeah, if for all y, all xy, this is true. And there's another condition which is called smoothness. So f is beta smooth if for all xy we can put an upper bound on how much this changes. Okay, so, and then I'll write one more definition, then I'll explain all the definitions. So one more definition. Gamma well conditioned so f is gamma well conditioned if it is alpha strongly convex and beta smooth for gamma is just going to be the ratio between alpha and beta. And notice this ratio is always less than 1, right? Because kind of if you're bigger than alpha and you're smaller than beta, then beta better be less than bigger than alpha, right? Okay, so I've written these definitions. These are great. These are useful for our proofs. But what do they really mean? Well, I told you that the stereotypical kind of convex function is the parabola. It's not the only convex function. There are other convex functions, like the exponential, e to the minus x, like this, right? Yeah, this is fine. I mean, the 0 is maybe here, x equals 0, but yeah. So e to the minus x is also a convex function, right? If I take any 2 points, the line connecting them is above the curve, right? But gradient descent will not work on something like e to the minus x. Does anyone see why? Right, there is no minimizer. That's one. Yeah? Right, that's the bigger issue, right? So like in all of this, we're working on bounded sets. We're working on sets that are bounded. But even if I work on a bounded set, right? If I work like really far in this region, notice that the gradient gets like shallower and shallower and shallower, and so my algorithm will not find a minimizer. It'll kind of get stuck. And so functions like this exist. And a kind of a key fact is that this function is not strongly convex. In fact, what does it mean to be strongly convex? Let me write an equivalent statement to well-conditionedness. If you're gamma well-conditioned with alpha strongly convexness and beta smoothness, then that means your Hessian is between, no over 2, beta I and alpha I. So what does being strongly convex mean? It means your curvature is at least alpha, right? Like what has curvature this? Like alpha x squared. So if this was like, let's say 1x squared, right? Maybe this is 0.5x squared. I should have brought colors. This is 2x squared. And so notice that this 1x squared is sandwiched in between this 0.5x squared and this 2x squared in terms of the actual function, but also in terms of curvature. And that's what strongly convexness is getting at, is that there's kind of a lower bound to curvature. Like you curve somewhat everywhere. And here, notice there's no parabola I can put to kind of match the curvature of e to the minus x everywhere, right? Like as we get further and further that way, the curvature kind of vanishes. And so this is what you should be thinking of as strong convexity. Strong convexity is like you have a parabola. Regular convexity, you could have things like this that are not as well behaved. And smoothness is the opposite. Smoothness is like there's a bound to how much curvature you can have. You can't curve like exceptionally large, because that could also be a problem for gradient descent, right? You might take a step that's too steep, that's too far. Yeah?
Would you like to quickly define what it means to have that relation?
Yeah, so this is the loaner order. Not too important. Easiest way to write this is a less than or equal to b is equivalent to saying that b minus a is positive semi-definite. So kind of another way to think about this is if let's focus on the right side, let's say. Or let's focus on the left side. So the left side says that the Hessian minus alpha I is positive semi-definite. So what does that mean about the eigenvalues of the Hessian? Does anyone want to speak up? What does it mean about the eigenvalues of the Hessian if this is positive semi-definite? Huh? What? Yeah. So a student just said that they are greater than or equal to alpha, which is correct, right? This is saying if I take my Hessian, subtract all its directions by alpha, I still get a PSD matrix. So even after all of that, I had non-negative eigenvalues. So therefore, the eigenvalues of this must be at least alpha. So again, it's kind of what I was saying. Like the curvature in all directions is at least alpha. Like it has some lower bound. And it's the same thing for the other side. Like the curvature in all directions is at most beta. The eigenvalue in each direction cannot grow more than beta. Not too important, this kind of subtle point, but the pictures are the more important thing. So I just want to pause for any questions, because it's a bit of a confusing concept. Yeah? Yeah. We will always pick parameters that are strictly positive. Yep. Wait, like you were saying, I'm saying alpha is like maybe the lower bound here. So yeah, alpha is 1 and beta is 4. Yeah, correct. Yeah. Capital A and B. I'm just saying, I was just defining, if you have two matrices A and B, A less equal to B means this. These are the equivalent statements. Okay. Great, so now we've defined a bunch of stuff. I've given you some intuition about what that stuff really means. I'm going to talk about one more theorem that's going to be important. It's also going to require a picture. And I'm going to try to fit all of the theorems that we need for the derivations on this board, so that I can use the other board to kind of cite this board. So hopefully I can do that. So down here, let me talk about the KKT conditions, or optimality conditions. So we know that, kind of from calculus class, right, that if I have unconstrained optimization, that is to say I want to find argmin x and Rn of a function right? That's equivalent to, if you're saying like x star is the arg min, that's equivalent to saying the gradient is 0 for a convex function. If f is convex and the gradient is 0, then we kind of know from like calculus, right, that that's the minimum. You found the minimum. But that's not true for unconstrained optimization, right? Sorry, for constrained optimization. By constrained, I mean you can't just pick x star from anywhere. You have to pick it from a convex set, a kind of a constraint. And so I'm going to erase this and write the generalized version of this theorem. So this is due to Karush-Kuhn and Tucker. I don't know when, like the 60s or something. So let K be a convex set, and let's x star be arg min over K, then, again, I'll say what this means in a second. The gradient makes a positive angle with y minus x star for all y in the convex set. All right, can everyone see down here? Is that okay? Okay. So what does this mean geometrically? Let me draw a decent picture, hopefully. So let's say my convex set looks like this. Little envelope kind of thing. And let's say my function happens to be optimized within, so this is K. Within K, my function happens to be optimized here. Okay? And let's let y be this point, somewhere in our convex set. And now what does this say? This says that if I take this arrow, and I take the arrow of the gradient of f, in other words, the direction of its greatest increase, then these two have a positive angle, an acute angle. They are correlated. In other words, I'm saying that moving towards any point in the convex set has a positive gradient, or yeah, a positive gradient. Or in other words, I'm saying that I will increase if I go along that direction. Yeah.
I'm not sure if this is true, but I remember reading in like doppler corners.
That's true if it's a linear function you're optimizing. Yeah, not in general. So a student asks, does it always have to be on the vertices, the optimizer? And the answer is no. Yeah. Like for example, if I'm trying to minimize the norm, and I'm over, I don't know, this object, and the origin is here, then the origin is the minimizer of the norm, right? Yeah. So, yeah. Cool. Yeah. It's in K. The constraint is on the points we can plug into F. F has to be convex, sorry. Yeah. Yeah. Yeah, I mean, basically every time I write F in this lecture, F is convex. Yeah. Whether it's strictly or whatever is different, but yeah. Just assume everywhere here is F is convex. Yeah. That's true, yeah. So Elijah pointed out that if the gradient of x is 0, then, sorry, if the gradient of x is non-zero, then the minimizer will land somewhere on the boundary. That's because, like, if you looked at the unconstrained version, right, like maybe like the true minimizer is over here, right, and we can't go over there because we're constrained to be in K. And so, like, you kind of will go to the closest point you can to minimize your function. But Yeah, that's not a necessary theorem for today. So thank you for bringing it up. Okay, great. That took a while. Okay. Any other questions? I'm going to erase this picture so we have lots of room. Okay. So now we can start actually proving some results about gradient descent. Cool. By the way, I'm giving all these theorems names so we can refer to them later. Makes your life easier, I think. So for, oh yeah, and then also we need to upgrade our gradient descent. So that's our basic gradient descent, which is unconstrained. Let's add in the constraint part, right? So currently I haven't forced x to be in the convex set yet. So let's do that. So I'm going to call this maybe yt plus 1. And then xt plus 1 is going to be, yeah, exactly, projection. So project into k, yt plus 1. Yeah, and then actually, for the results we're gonna prove, we're actually gonna prove last iterate convergence. So we're really gonna prove that the last thing that you get is actually good, because we're working in a very special setting now. Hmm?
It shouldn't be x sub.
No. Because, oh, I see. Yes. Sorry. Yes. Thank you. Great. Now, let's write the theorem. So we're going to choose a specific step size, but it's going to be constant. Okay? So what am I saying? I'm saying that after t steps, I exponentially decrease my distance from the optimizer. Mm-hmm.
So the one over beta, the beta is the smooth.
Yes, correct. Yeah, so whenever I write gamma well conditioned, assume there's an alpha and beta, alpha strongly convexity, and beta smoothness that I'm not writing down, but is there. And actually, I'm going to even remove this norm. Because we're happy if h is negative, by the way, right? Actually, h can't be negative, but right, because the optimizer is the minimal value. Okay. So let's prove, yeah, what's up? Yeah, that's true, but we're putting an upper bound on h, so it's okay. Sure, but we're arguing about ht plus 1, right? Ht plus 1 is upper bounded by something, right? It's upper bounded by 5. Then it could be 0, it could be -5, it could be -10. I'm okay with that. So don't worry too much about this point. Just the error is decreasing. Give me an idea. Okay, great. So let's do the proof. Now the proof is going to be great if we're just going to spam all the definitions we've learned already. So xt plus 1 is this. I'm going to define, as Professor did before, this. Just as ease of notation. Okay, so we have this. Now this is equal to x minus the point we're projecting. So we're finding the closest point in K to the point we're projecting. And then now, as a homework exercise, which I hope you will do, this is equal to argument x and k, gradient dot the difference in x's plus 1 over 2a to t. Yeah. So these are two equivalent optimization problems, and this is by exercise, I think 6 or something in your homework, so hopefully you do it. Great. So now let's track how h changes. So h, which is just the difference in function values. The difference in h is the same as the difference in function values by definition. And then by smoothness, right? We're going to use smoothness. The difference between f of y and f of x is at most the gradient at the base point, which is just delta t, times the transpose the difference, plus this beta over 2 norm term. Okay. Now this is, by this, at most, yep. So because minimizing xt plus 1 is the thing that minimizes this quantity, so therefore if I plug in xt plus 1 here, it's definitely smaller than plugging in any x here. And then now we can apply the other side, the alpha well-conditionedness. So the alpha well-conditionedness, we'll put a bound on this term, right? If you look at the well-conditionedness, the gradient times the amount of times the difference is at most the difference in the f values minus, because we're trying to isolate the gradient term for the strong convexity. So we need to bring the alpha term over on the left. So minus alpha over 2 x minus this plus beta over 2. Cool. And here we just applied alpha well-conditionedness. Sorry, alpha strongly convex. Okay. Great. Yeah.
For the second to the last,
Mm-hmm.
is it technically?
Yes. But I added the minimization term, so then that way I could put it here.
But I mean, like, it's equal.
It is equal to this, yes.
First, they're equal to the second, equal to the previous.
Yeah, yeah. These are equal because xt plus 1 is defined as the minimizer of this expression. Yeah. And notice that eta t is 1 over beta. So that's where the simplification is coming from. Yeah, maybe let me write that out. Yeah, so this is saying xt plus 1 is the minimizer of this expression. Oh, we have this expression right here. We have this expression right here. And so therefore, this expression must be minimized by xt plus 1. So it is the minimum. So I guess I should write this equality here. Cool. Awesome. Let's keep going. So now I said I could pick any x I want here, right? And it's less than or equal to the minimum of those x's, right? So I'm going to pick the following. I'm going to pick an x of the form it's on the line between xt and x star, right? Obviously, such an x is in K because K is a convex set. We're working over convex set here, K. Yeah? Yes. We're going to pick a value of mu that makes this nice. Okay? Okay, now continuing this. The difference in the errors is at most, let's just plug in our value of f. And I'm going to simplify this into one fraction, beta minus alpha over 2. And then now if I subtract x and xt, we should get rid of this 1, right? Right. When we subtract x and xt, and over here, we'll get rid of this 1, and we'll be left with norm of like so. Okay. Cool. And then what can we do here? Does anyone have any ideas on how we can tackle this term? Yeah, many students have said use convexity. So by Jensen's inequality, this is at most 1 minus mu f of xt plus mu f of x star. This is by convexity. Okay. And we still have this term here. Okay, great. And now we have a cancellation with this one and this one, right? So we had the cancellation before with x minus xt. Now we have another cancellation. So this and this get canceled out. And now notice the following. Notice that what do you have left? You have mu times f of x star minus f of xt. So that's negative h, right? By the definition of h, that's negative h. Right? The difference between optimal and what we have. And furthermore, we can factor out a mu from this part, right? Factoring out a mu with the square gives us mu squared. After we factor out the mu, we're left with just x star minus xt. Okay. Cool. Okay, we're almost done, I promise. So now we have the difference in terms of the previous. We can do one more thing. We can get rid of this term. And to get rid of this term, we're going to use strong convexity once again. So h of t is just the difference, right? So again, we can lower bound this difference with strong convexity, the gradient. Okay, alpha strong convexity. And then, this almost looks like this, except there's this pesky term in the way. But we know by KKT conditions that this term is non-negative, right? This is non-negative by the KKT conditions over there. So I can just remove this term. Whew, okay, good. Great, so now we have this left-hand side in terms of ht, and then now we can rewrite this in terms of ht. So let's do it. So this term right here is at most 2 ht over alpha, right, if we just flip this. So I'm going to erase this term. I'm going to put 2 ht over alpha. Great, and that's the only reason we'll need this this derivation. So I'm just going to erase it so we can finish the proof here. Yep. Any questions up till now? I know it's a very long proof, hard to follow, lots of steps. But please stop me if there's any step that's unclear. Okay. So let's erase this. And now we'll just finish up. So now we can just factor out the ht. Okay. And now we want to make this inequality as small as possible. I'll save you the quadratic equation. I'll just tell you what the minimum is. But I'm sure you could do it on your own. So this will be negative alpha over beta minus alpha ht. Oof, okay. So this was choice of mu. Okay. All right, so now we know that the difference is at most this. So finally, ht plus 1 is at most, put the 1 over there. Okay. And now beta minus alpha is smaller than beta, right? Because alpha is positive. So I can, if I increase beta, then that's going to decrease 1 over beta, which is going to increase negative 1 over beta. So the inequality goes in the right direction to just remove this. And we know from our first lecture that we can use e to the minus to upper bound this. Okay. And now since we decrease by e to the minus, this is gamma, right? This is the same as gamma. E to the minus gamma over 4, and we do that every time step. After t time steps, we'll get the rate that we had claimed. Cool, so let's go back through the proof and just make sure we followed all the steps that were going on. So going back through the proof, I promise you, not all of the class is this dry. Today is very dry. So what was the proof? The proof was first, we took xt plus 1, the next iterate. We just wrote out its definition, and we wrote down an equivalent minimization form for it. And this equivalent minimization form is in your homework. It's not too hard to prove, I promise. Then we looked at the difference between the error at t plus 1 and the error at t, and we wanted to track how it grew or shrank. And we did just that. Then we applied this beta smooth convexity to compare the difference in function values to the gradient. Then we had noticed that this gradient plus beta over 2 function, by our choice of step size, is exactly the same thing that xt plus 1 minimizes. Xt plus 1 was perfectly chosen to minimize this beta smooth objective. And so we could just plug it, we could just minimize over that. Then we expanded the gradient using alpha strong convexity, because we wanted an upper bound on the gradient. So alpha strong convexity gave us an upper bound on the gradient as this expression. Then we, we're free in our choice of kind of x, and we chose x to be something a little bit nicer. We chose x to be on the line between xt and x star, because we noticed we had this f of xt here that we wanted to kind of cancel out. So we chose it on this line. And once we chose it on this line, we could apply Jensen's, the definition of convexity. After some simplification and a clever choice of mu, I promise you this choice of mu will give you this. Then we arrived at that the error was decreasing geometrically. It was increasing according to this rate. And if I iterate it t times, it's decreasing exponentially. Cool. Any questions? Yeah? These two? So xt plus 1 is the argument of this expression. And this is beta over 2, right, by our choice. So since xt plus 1 is the argument of this expression, if I plug in any x, it's only bigger. So it's equal to the minimum. Yeah. Great question. Okay. Great. So now I'm going to erase this proof, but we're going to use that theorem again. Because now I've told you that gradient descent converges for these gamma well-conditioned functions. Like who cares about gamma well-conditioned functions? Why can't we do it for all functions, right? So it turns out we can, and there's a certain amount of reductions we need to do to make the function well-conditioned. Okay, yeah?
Is it always going to be well-conditioned? The domain bound?
No. Like e to the minus x is not well-conditioned, even though the domain is bounded. right? There's no kind of parabola you can draw that matches the curvature.
But if the domain's bounded,
Yeah.
then like you can find the minimum.
Yeah, you can find the minimum, but it doesn't, like if you take the Hessian, it doesn't satisfy our definition, does it? Right, but we're talking about constrained optimization here. Anyways, there are other functions which are convex everywhere and on a bounded domain, and you still don't have strong convexity. So yeah. Okay. So So what are the two barriers to not being well conditioned? So the first one is strong convexity, and the second one is smoothness. So first, let's see how to make any function strongly convex. Okay? Okay, so claim. Actually, I'll write the claim over here. I'll write it here for now. So claim, if f is beta smooth and convex, then this function is strongly convex. It is alpha prime strongly convex, and beta plus alpha tilde smooth. Okay, so what is this saying? This is saying I can take f, I can add this small term, and now this new function is strongly convex. You may have seen a term like this if you study the theory of regularization, right? This is what people call L2 regularization. But for our purposes, it's just making the function strongly convex. So kind of I'm taking my original function and I'm adding a small parabola to it to make it kind of have positive curvature. This claim is a homework exercise, so have fun. Okay, I have another claim. Here. So algo 1 with run with G So algorithm 1 run with G, of course we know how it's going to react because of that. But algorithm 1 run with G, let's say let x1, x2, xt be iterates of algo 1 run on G, then the convergence rate is given by this. Yeah, what's up? Yes. Whatever I have written up there. Yeah. With choice of alpha tilde being this. Where d is, again, the diameter that we talked about last time, the furthest distance of 2 points in our set. And this theorem is not too hard, so let's just do it. The claim is, I think, harder, and so you guys are going to have fun in your homework. Okay, so proof of theorem. Again, I'm going to define this to be h of t, just to be simple. So what is h of t in terms of g? Well, it's f of xt, so that's g of xt minus this term. And then that's f of xt. G of xt is, sorry, f of x star is g of x star minus the same thing for x star. Great. So this is equal to just subtracting the two. And subtracting these two. Okay. So this first one, by our theorem, this is at most h1 of g times e to the minus gamma t over 4. What is gamma? Well, for g, it's alpha strongly convex and beta smooth, beta plus alpha smooth. So it's alpha over beta plus alpha well conditioned times t over 4. So now this is just me using the guarantee of that WC conv theorem. Now this other term, any ideas on how to deal with these two? Yeah? Sorry. Yeah. This one. Yep. Nice. So any ideas on how to deal with this term? Yeah? Yeah, we can use the diameter bound. So I guess this term only helps us, so there's only d squared. Good? Okay. And now finally, right, we had alpha prime, alpha tilde we could choose. And I claim that this choice of alpha tilde is the optimal one. Again, I'm not going to make you prove it right now. And when you simplify, what you get is O of this. So I'm simplifying this. This part is just a constant, right? This is some constant that's independent of, like we're just ignoring any constants. We're purely focused on the dependence between t and beta. Yeah. This one? Yeah, so this is g of xt minus g of x star. What does the theorem say? It says the difference in the function's value at t and the optimal value decreases exponentially like this. So I just plugged in, this is h1 for g. And this is the exponential rate we were guaranteed. And this is the gamma, based on the claim that I wrote up here. Yeah, wherever it is. Yeah. This thing. Hmm?
Why is the optimal choice for alpha not dependent? The g of x.
Oh, this? It does. We're just thinking of this as a constant. Like, we're thinking of this as a constant in big O.
But it's not in the expression.
Yeah. We're thinking of this as like, as some constant whose value we don't care about. And we could just like factor it out and just focus on minimizing this sum.
Right, but like the optimal choice for alpha tilde should depend on it.
Yeah, I agree. But we're suppressing the fact that this constant matters. Like I'm saying, imagine calling this just like k, right? And so this is equal to k e to the whatever plus alpha tilde over 2. Like this is some, I don't know, function of alpha. Right, this, right? Now I could just factor out k, right? And just ignore it altogether. Like just think of it as a constant.
I guess like the choice of the optimal alpha tilde should depend on it.
Yeah, like I think there might be some, this might be an O. Yeah, I think this is an O. Yeah, that makes sense. Yeah. So the constant is like maybe there's some constant with this 2 that also matters. Yeah. It's not too important. Kind of we want the right asymptotic, and to get the right asymptotic, we can choose some alpha in that ballpark. You can work out the details of the exact alpha. Yeah. Correct. So if you're using this in practice, you're never like computing this function and like saying alpha is set to this. You're just tuning it. You're just like saying, okay, if I try 10, what happens? If I try 1,000, what happens? Yeah. So.
I guess this logic is responsive for
Uh-huh. Yeah, I think you're right. I'm not 100% sure. I'll have to think about this. Yeah. Uh-huh. Correct. This is a whole literature called preconditioning. There are lots of differing opinions on how to do this. It just, for right now, what I've written here works for any x naught in our set. So, yeah, but there are lots of schools of thought what you should do. Some people say, oh, you should pick like the middle of your convex set. Some people say, oh, you should pick like you should do some pre-optimization and pick something and then do it this regularization. Yeah. In practice, everyone just uses 0 for x0. Yeah, so. Mm-hmm. Yes. Right. As the people running the algorithm, we're not running it on F. We're running it on G, and we chose the alpha that makes our analysis work. Yeah. Yeah. I'm not 100% sure about this constant thing. I think you're right. There's some constant dependence that was suppressed. Yeah. Yeah. D is the diameter of the set. It's the maximum distance between any 2 points in the set. So it's an upper bound on this term and I guess this term. Yeah.
get the plus alpha tilde and
This theorem. If your alpha, yeah. When you add this, you actually change the smoothness too. Yeah. Which is what we'll expect from the definition of smoothness, right? Yeah.
So in some sense, like you need to change your alpha tilde for different.
Yes, yes. This is true in a lot of practical algorithms too. Like think about like if you know Atom or if you know these other optimizers. Like on different data sets, when you have like let's say you're training a neural network, you'll train for different amounts of time based on how much data you have available, right? And based on the amount of data you have available, your learning rate and like the things you choose changes. So this is another kind of consequence that we see mathematically.
When you change it for every iteration.
No,
I just said it in the beginning.
you said in the beginning. You know I have T is going to be like 10,000. I have like 10,000 images I'm going to train on, and I'm just going to let it rip. Yeah. Yeah. Sorry, which decision maker?
Or like the algorithm.
Yeah.
Does it know?
I guess you're only given the gradient of f of x. No, that's a very hard problem. Right? If f is a big neural network, it's a very hard problem. Yeah. And also, like we said, when we're doing constrained minimization, gradient of f equals 0 is not even sufficient to find a minimum, right? Like, you might not have gradient f equals 0 anywhere, and you might have to do something else. Yeah. All right, cool. Okay. Now let's talk about the other direction. So I told you how to make any function strongly convex. Let me teach you how to make any function smooth. Okay? So we can do the following. Let f delta hat of x be expectation v over b. What is b? B is going to be the ball of dimension d. So we've been working with a function that takes inputs in Rd and turns them into real numbers. This is the ball of radius 1 of dimension d. Okay? So what did I just write here? What does this mean? It means I'm making a new function which has the following property. To find out at any point x what the value of this new function is, you look in a small ball of radius delta around x, and you average the value of the function over this small interval. And this smoothens out the function. In fact, if you've ever heard of blurring, this is what blurring is in image processing, is you take a small patch of the image and you average all the pixels together in that part of the image. And you do that for every single pixel. Every pixel is like the average of its 8 neighbors or something. So this is our kind of smoothing operator. And here's a theorem. Here's many theorems, actually. So f delta has the following. So property 1, if f is alpha strongly convex, then so is f delta hat. Furthermore, f delta hat is always smooth. Here g is again the Lipschitz constant of f. And 3, the distance between the smooth version and the original version, it turns out they don't differ too much. So what am I doing? I'm saying that, f delta is a good approximation for f. And f delta is smooth. And f delta is, strongly convex if the original thing was. So now I have the perfect thing to use for gradient descent, right? Now I can apply my theorem again. So we're going to run algo 1 final time on f delta. Let's x1 through xt be the iterates. Then okay, lots of variables here. Yeah, what's up?
So does this require that f is G Lipschitz?
Yes. So yeah, so again, as I wrote before, we're going to assume that f is G Lipschitz for kind of everything. So yeah, this is upper bound on the error. Again, notice it's going to 0 as t goes to infinity. That's the main thing. And, yeah?
What's the little d?
Little d is the dimension of the space. Yeah, so f is from, I guess I didn't write that anywhere. F is from Rd to R. Okay? All right. That's delta. Okay, I don't think I'm going to have time to prove these lemmas to you. They're very interesting. I think we'll kind of return to why these lemmas are important when we talk about bandit convex optimization. But let's at least tell you the proof of the main theorem. And it's not too hard. It's just the same statement as before. Only now, notice that f of xt is within delta g of f delta. So if we would turn these into f deltas, we incur a loss of delta g and maybe another delta g. So 2 delta g error total. So in other words, this is at most this plus 2 delta g, because we have an error of delta g on each term. And then we just apply our theorem. Again, we apply the well-conditionedness theorem, which states that this is at most f delta of x1 minus f delta of x star e to the minus gamma t over 4 plus 2 delta g. And that's pretty much it. Once we have, kind of this thing, all we have to do is just choose our parameters, choose our smoothness parameter effectively, because remember, gamma also depends on delta. I guess I can write the dependence. Let's just call this H1 delta, just for ease of notation. Right. The only free parameter in this equation is delta. Right. We have no other free parameters, and I guarantee you that this choice of delta will give you O of dg squared log t over alpha t. Okay. This was not a very long derivation. This was very similar to the other derivations. But any questions? This is the main step, I think, from here to here. Yeah. F is alpha strongly convex. Yeah. Mm-hmm.
We showed that we can run gradient descent, but alpha is strongly convex, but not smooth.
Yeah.
One beta is smooth.
Yeah.
Alpha is smooth.
Uh-huh.
If it's neither,
Do both.
both.
So add the regularization term and do the smoothing. Yeah, so that means if you have any convex f, you can turn it into something close, use gradient descent to find the minimum, and then that's close to a minimum for the original function. Yeah? I think it shouldn't matter, right? Because we have this theorem, right? Oh, but you're saying you need smoothness to prove the other theorem? I don't think that's true. I think when you add the extra term, it does become strongly convex. The theorem I wrote just was stronger. It was saying that if you're smooth, then the new smoothness of this parameter. Yeah. I think either order is fine. Yeah, I want to say either order is fine. Yeah, exactly. Yeah. Good question. So how do you get the gradient? Right? So I'm asking a bit of a funny question, but we'll see later in bandit convex optimization, a way in which you might estimate this expectation, right? Because if you really dig deep and dig carefully into the algorithm, you don't even need this function, right? You only need the gradient. And furthermore, if you dig further, you'll see that you don't even need the gradient. You just need a random variable whose mean is the actual gradient. This suffices. This is called stochastic gradient descent. And I think Professor Hazan will go over it more in the future. But yeah, great question. Anything else? Yeah. This step to this step. So for each point in the space, f delta at that point is within delta g of f. Yeah? So f delta at this point is within delta g of this f, and f delta is within delta g of this f. So together we have an error of 2 delta g. Okay, unfortunately I did not get to prove this theorem to you guys. I guess let me write one equation and then you're free to go. So the equation that maybe is the first step to proving this is true is the following. So S is the sphere, B was the ball, S is the sphere, it's just the surface. And this is the first step in proving that this function is smooth. And if you want to know how to derive this, this is some consequence of Stokes' theorem. So I encourage you to go home, think about it, and think about why that integrating over the ball and integrating over the sphere might be related. All right, that's it for now. Thanks.